So welcome to lecture 10. In this lecture we will continue our study of rigid body kinematics. Half the lecture will be spent upon examples of velocity analysis and the remaining half will be spent in deriving the very important 5-term acceleration formula and beginning the applications of this formula. So a quick note as to where we are headed. What we are trying to develop is kinematic analysis of systems consisting of many connected rigid bodies. Kinematics consists of velocity, acceleration, angular velocity and angular acceleration of the rigid bodies. It has two steps fundamentally. The first step is the velocity analysis, in which we find the velocities and angular velocities of the component rigid bodies. The velocity analysis is followed by the acceleration analysis, in which we find accelerations and angular accelerations of the rigid bodies that comprise the system that we are studying. So in this lecture we take the first step and we do the velocity analysis. We see how that is done, and in the subsequent lecture we will do the acceleration analysis. So let's begin. So the best way to understand velocity analysis is to do it through examples, and I will do 2 examples and I will encourage you to do many more. So example 1. The example 1 consists of this mechanism in which there is a screw which is turning, and as it is turning it is driving this collar C up and down. Okay, in this picture it is going down at the velocity Vb. As the collar comes down, it drags this pin B down with it, and because the pin B is contained in this slot of this arm, it rotates the arm downwards, or maybe it could be going upwards, who knows. And we are supposed to find the angular velocity of the slotted arm. The angular velocity will possibly change as the collar comes down, so we are supposed to find the angular velocity when this angle is 30 degrees. The other information given to us is the distance between the screw and the pin O, which is given to be D. So let's go ahead and solve this problem. So there is a general strategy for the kinematic analysis of connected rigid body systems. First of all, you must agree that this is a connected rigid body system. You have the slotted arm which is connected at O to the ground. The ground is also a rigid body. To the ground there is a shaft on which the collar C, which is also a rigid body, can slide up and down, and the collar C is connected through the pin B to the slotted arm. So it's a connected rigid body system. Connections impose kinematic constraints. So for example, with respect to the slotted arm, this pin B will always seem to be moving in the slot. The collar C can only slide up and down the shaft, the vertical shaft. So usually in these systems, partial kinematic information is available for each rigid body. So for the slotted arm, we know that it can move only in the plane. I never said this is a 2D problem, it could be a 3D problem, but from the figure it is clear that the slotted arm can move only in the plane. The point O of the arm is fixed to the ground, has 0 velocity, and the collar C is constrained to move vertically up and down. Knowing this, what is done is that we find a convenient point and we write the motion of that convenient point in 2 different ways, maybe with respect to 2 rigid bodies, and then we equate the way we have written the motion of this point and thereby solve the problem. So for example, point B here, which is the pin on the collar C, we know its velocity, it is going up and down at velocity Vb. But the velocity of the point B can also be investigated by sitting on the slotted arm. And when we write the velocity of B in this way, we get another expression for it. And we can compare these 2 expressions of the velocity of B and then get the missing information. This is the general strategy. And I will now implement it, and hopefully that will make it clearer. So over here on the right I have redrawn the connected rigid body system, and I have also put in some coordinate systems. What are these coordinate systems? The blue one is the BFCS for the slotted arm, and as usual I will encode it with unit vectors E1, E2, E3 is out of the plane. Similarly, I also have the coordinate system which is fixed to the ground, which is the green coordinate system, which is described by the unit vectors capital E1 and capital E2. Okay, and let me also give this point a name. Let me call this as G. Okay, so now what shall we do? As I said, the strategy is first to find a convenient point, and over here in this picture you will agree that a convenient point is point B. Usually convenient points are at the intersection of two rigid bodies. We are trying to understand the motion of the rigid body, which is the slotted arm. So we should look at how the slotted arm connects to the collar, which we know, and it connects to the point B, the pin B. So the pin B is a convenient point to investigate. So we already know that coming from this direction, the velocity of B is VB in the minus E2 direction. Okay, so this is one way to write the velocity of B. So we now need to write the velocity of B in a second way. What we will do then is sit on the BFCS of the slotted arm, which I have called E, and observe the motion of B, and then try and relate that observation to the velocity of B that it has with respect to the ground fixed frame, which I have called E0. Immediately we see that we need to relate the observation in a rotating frame, this is a rotating frame, with an observer frame, and we have developed a formula for this in the previous lecture, which I shall now recall. So suppose we have an observer frame E0 centered at O with velocities with unit vectors EI, and a rotating frame, usually the BFCS of a rigid body, given by E centered at G with unit vectors EI, and both these frames observe a point P. Then the velocity of P in the observer frame is the velocity of P relative to the BFCS. So this was the BFCS and this was the observer frame, plus the angular velocity of E with respect to E0 cross the location of the point P with respect to the origin of the BFCS, plus the velocity of the origin of the BFCS with respect to the observer. So this is the formula that we intend to use. To use this formula, it will be necessary to identify the various P, E, E0, G, O with the points in this picture. So let's do that. So when we compare this formula with this picture, it is clear that the point P is really B. The angular velocity of E with respect to E0 is really the angular velocity of the slotted arm, omega arm. The point G is O and O is G, so they have been swapped in the picture. So with these identifications, let's go ahead and write down this formula as applicable to this picture. Okay. So VB will be VB rel plus omega arm cross RP with respect to O plus VO with respect to G. G and O have been swapped. So far we have not tried to leverage or implement the various kinematic constraints that are clear in this problem. So what do I mean by that? Well, for example, this is a 2D problem. What that means is the slotted arm moves in the plane. That means omega arm is really a scalar along E3. E3 was out of the paper. The point O is fixed with respect to G. So in the observer frame, O remains fixed. That means VOG is 0. So with these we can write down this formula as VB is VB rel plus omega E3 cross, what is RPO? Well, it's not RPO, it's RBO. RBO is, so it is this distance along E2. This distance is d upon cos theta. So I will write that down here, that RBO is d upon cosine theta along E2. That's what comes over here. Okay, so now I have written down the velocity of B in two different ways. Here is one way, here is another way. So let's go ahead and combine them. And when I do that, I will get VB along capital E2 must be VB rel minus omega d over cosine theta along E1. So have we solved the problem? Well, we have got an equation. Let's see how many things we know. I know VB, that's given to me. I don't know omega, and it seems that I do not know VB rel, because really even if you were sitting in the slotted arm, with the slotted arm, you would not know how fast this point B is moving. So if you do a number counting, seems to be that you have three unknowns, scalar omega and a vector VB rel. It's a planar problem because B will move in the plane, so VB along E3 is 0. So VB rel is two unknowns, and that's 1, so that's three unknowns. You have a equation in which the E3 component is not there, so it's a planar equation, so it's only two equations. So you have three unknowns, two equations. That means we can't solve the problem. So what have we missed? Well, let's now think a little bit more. Do I know anything about VB rel? Remember, it's a vector, so it is possible that we may know the magnitude but not the direction, or we may know the direction and not the magnitude. Let's think about it. VB rel is the velocity that B will appear to have if you were sitting in the blue frame. If I was sitting in the blue frame and rotating with it, it will look to me that the point B is always moving along this line. That means VB rel will be a vector along E2 always. So let's write this information down, that VB rel is actually some unknown V rel along E2. Notice what happened. This had two unknowns, but now I am saying I actually know the direction, so it has reduced from two unknowns to one unknown. Now I have, if I now put this together, I have the equation VBE2 is equal to V rel small e2 minus omega d over cosine theta small e1. In this equation, I have one unknown, two unknown, and these are two equations, so therefore I can solve this problem. What am I after? So we want omega. We are not currently interested in V rel. Now I will caution you, there's capital E2 here, but there's small e2, small e1, so please do not equate this and this. They are different vectors, right? Capital E2 is this vector, small e2 is that vector. They are not parallel. So we want omega. So the quickest way to get omega is to take this equation, which let me call it star, and project it along E1. So if I do that, then this quantity will drop out and I will get the formula VB capital E2 dot small e1 is equal to minus omega d cosine theta. So this tells me that I can get omega by taking d cosine theta onto this side. I need to still compute E2 dot E1. Well, that is easy. This is E2, that is E1. So E2 is this direction. That angle is same as this angle. So this is also theta, right? So E2 dot small e1 is simply cosine theta. So back over here, this will tell me that omega is minus VB cosine square theta over capital D. There, I have solved the problem. I know VB, I know D, and theta is given to be 30 degrees. So over here, cosine square theta will be 3 over 4. So that's my answer. I mentioned at the beginning of the problem that omega may change, and indeed as theta changes, omega will change even if the point B or the collar C comes down at a constant speed. The angular velocity of the slotted arm will change with theta. So that's the answer. Let's move on to another example.